For this problem, we're going to find f plus g, f minus g, f times g, and f divided by g and their domains. So we'll start by finding f plus g, f minus g, f times g, and f divided by g. So in this first example, f is the square root of 16 minus x squared, and g is the square root of x plus 3. So to find f plus g, what we want to do is simply add these two functions together. So we'll have the square root of 16 minus x squared plus the square root of x plus 3. Now, the only time we can add two square roots is if whatever is under the square root is the same. In this case, we do not have that, so this is the simplest way to write your answer. For f minus g, we do the same thing as f plus g, except we're going to take a difference. So we'll have the square root of 16 minus x squared minus the square root of x plus 3. Once again, these two square roots are very different, so we can't combine them any more than this, and this would be our final answer. For f times g, we're going to multiply our two functions. So we'll have the square root of 16 minus x squared times the square root of x plus 3. Now when you multiply two square roots, you can multiply the two things under the square root and write it as a single square root. So we can say this is the square root of 16 minus x squared times x plus 3. To finish out our answer, we can simply multiply these two factors together. So we get the square root of 16x minus x cubed plus 48 minus 3x squared. And this is our simplest answer. For f divided by g, we simply take the function f, so the square root of 16 minus x squared, divided by the function g, so the square root of x plus 3. Just like with multiplication, when you divide two square roots, we can combine these into a single square root with a fraction on the inside. So we can say that this is the square root of 16 minus x squared over x plus 3. Now this is the simplest we can get this because x plus 3 does not divide 16 minus x squared. So these are our four functions, f plus g, f minus g, f times g, and f divided by g. Now we're going to find their domains. So for the domains of these function operations, what we want to think about is the domain of f, the domain of g, and where they intersect, so where those intervals overlap. So first, let's find the domain of f of x. So to do this, we know that square roots cannot have negative numbers under them, so we take 16 minus x squared, and we set it greater than or equal to 0. Now we can factor this and get 4 minus x times 4 plus x is greater than or equal to 0. And what this tells us is that x must be between -4 and 4. So the domain of f is going to be -4 to 4. Now for the domain of g, we can do the same thing and say that x plus 3 must be greater than or equal to 0. And subtracting the 3 over, we get that x must be greater than or equal to -3. In interval notation, we can write this as -3 with a bracket up to positive infinity. Okay, so we have our two individual domains, and now we want to figure out where do these two intervals overlap. Well, if you think about the smallest point we can have, we know that -3 is inside of this other interval. So basically what we want to do is chop off everything to the left of -3. So our domain is going to start at -3. And then the biggest number we can have must be 4, because this domain here goes to infinity, but of course infinity is a lot bigger than 4. So we want to just stop at 4. And so our domain should be -3 to 4. Now the domain for f plus g, f minus g, and f times g will all be the same. So these are all -3 to +4 with brackets. For f divided by g, we simply have to take into consideration the points where our denominator could be 0. The only place this could happen is if x is equal to -3. So you can imagine plugging in -3 to x plus 3, and that would give you a denominator of 0. So unlike how we had a bracket in the other three domains, the only difference with f over g is that we no longer want to include -3, so we'll just put a parenthesis around it instead of a bracket. So let's try another problem like this with some fractions. So once again, we're going to find f plus g, f minus g, f times g, and f divided by g and their domains. So for f plus g, we simply want to add f and g. So we'll have 2 over x plus 4 over x plus 4. And we can simplify this a little bit. So to get a least common denominator, we just want to multiply our two denominators. So we'll have a single fraction with the denominator of x times x plus 4. Now we can think about what is going to happen to the tops of our fractions. So for the first fraction, since we multiplied x by x plus 4 on the bottom, we'll have to multiply 2 by x plus 4 on the top. And for the second fraction, we multiplied x plus 4 by x on the bottom, so we want to multiply by x on the top. And so if we simplify this a little bit, we should get 2x plus 8 plus 4x over x times x plus 4, which gives us 6x plus 8 over x times x plus 4. For f minus g, we do the same thing, except we want to subtract. So we'll have 2 over x minus 4 over x plus 4. And if we do this subtraction again, we'll have a least common denominator of x times x plus 4. And then we multiplied 2 by the x plus 4, and then we multiply 4 by x. So what we end up with is we get 2x plus 8 minus 4x over x times x plus 4, which if we go one step further would give us negative 2x plus 8 over x times x plus 4. For f times g, we want to multiply the two fractions. So we have 2 over x times 4 over x plus 4. So when you multiply fractions, you want to multiply across the top and multiply across the bottom. So what this gives us is 8 over x times x plus 4. And finally, for f divided by g, we'll have 2 over x divided by 4 over x plus 4. So remember, to divide two fractions, we want to take the bottom fraction and flip it and multiply. So we have 2 over x times x plus 4 over 4. 2 goes into 2 one time, 2 goes into 4 twice. So what we get is x plus 4 over 2x. So those are all four of our functions that we needed to find. And now we can find their domains. So once again, we're going to start by finding the domains of f and g. So for f, our main problem with the function f is, can the denominator equal 0? The answer to that is yes. And the one place that can happen is if x is equal to 0. So basically what we want to do is take the entire number line from -infinity to +infinity, and we want to exclude that single point at 0. So the domain of f will be -infinity to 0 with 0 to infinity. So that's for this guy right here. And then the domain for the second function is going to be your entire real line, but you want to exclude that point where x plus 4 will equal 0. So the only number that can make x plus 4 equal to 0 is -4. So we want to start at -infinity, go up to -4, and then go -4 to infinity. Notice that I'm using parentheses on all of these intervals because we want to make sure we exclude those points. Okay, so now we want to think about where our intervals overlap. So we can imagine starting at -infinity because both of our intervals have that, and then the first point we're going to hit is -4. So that interval is sort of the same. But then, after -4, rather than just going all the way to infinity, we have another problem at 0. So this is going to give us an interval from -4 to 0, and then we can finish it up by saying 0 to infinity, because we don't have any problems after that. So this big interval here is your domain for f plus g, f minus g, and f of g. So for all three of these, you'll have that same answer. For f over g, we also have to consider if there's an extra point where the denominator of this function here is equal to 0. And we see that our denominator is just 2x, so 2x equals 0 if x is equal to 0, but we already excluded that point. So actually in this case, f over g has the same answer as the other three. So we have the same answer right here, but you always have to check and make sure. That will not always be the case. Okay, so for this next example, we're not going to find all the functions again. We're simply going to find the domain. So this time our function is the square root of x plus the square root of 2 minus x. So this is the same idea as before. Basically what you can imagine is that pretend like we have a function g of x called the square root of x, and pretend we have an h of x that's the square root of 2 minus x. So we can imagine f of x is like g plus h, because we just added the two square roots. So it's the same process that we used for the other examples. So the first thing we want to do is figure out what is the domain of the square root of x. Well, we know that we can't have negative numbers under the square root, but 0 is okay, as are all the positive numbers. So our domain should be 0 up to positive infinity, and notice that we include 0 with a bracket because we can have the square root of 0. That's just 0. For h of x, we want to do the same thing, but maybe we want to write an equation this time just to make sure our work is okay. So we want to make sure that that thing under the square root is bigger than or equal to 0. So we write that as 2 minus x is greater than or equal to 0. And then what we can do is just move the x over. So we have 2 is greater than or equal to x, which if we switch this around means that x is less than or equal to 2. How do we write this as an interval? Well, we'd start at negative infinity and go up to positive 2. And we include positive 2 because we had an equal sign on our inequality. So those are our two individual domains. And now all we want to do is see where these overlap each other. So the smallest number in our intervals is negative infinity, but our interval over here doesn't take those numbers into account. So the smallest number that's in both intervals is 0. So our overall domain, I'm going to write this as d sub f, just so you know it's the domain of f. So we know it has to start at 0 because that's the smallest number that's in both intervals. And now the biggest number that's in both intervals is 2. So notice we have every number bigger than 0 in this first one, but we only go up to 2 in this second one. So our domain must be 0 to 2. So this would be your final answer. In this next example, we're going to switch gears a little bit and go to composite functions. So instead of adding and subtracting functions or multiplying or dividing, what we're going to do now is substitute entire functions into each other. So for this example, we want to find f of g of x, g of f of x, f of x, g of x, and their domains. So we're given that f of x is x over x plus 4, and g of x is 7x minus 4. So first, we're going to find f of g of x, which if you recall is just f with g plugged into it. So that's another way to write that. So we're going to take the function f, and everywhere you see an x, we're going to put the function g. So I've left these as little blanks. So on the top, we'll have 7x minus 4, and on the bottom, we'll put a 7x minus 4 in the place of x. So that is f of g of x. For g of f of x, we're going to go backwards, and we're going to plug f into g. So you can think of it like this. So we're going to have 7 with f plugged in minus 4. And so if we plug f into the parentheses, we'll have x over x plus 4. So this function is g of f of x. Now for f of x, we want to plug f into itself. So we can imagine it like this. And what this will give us is something extremely complicated. So we know we're going to have a big fraction. On the top we have an x, so we're going to rewrite the function f in place of that x. And on the bottom we have an x, so we're going to rewrite f again, and then a plus 4. So this would be f of x. And finally, we have g of x, which is if we plug g into itself. So this would be 7 times 7x minus 4 minus 4. Like that. So it's not always a good idea to simplify these. Notice that we simplified the operation questions a lot more than these composite questions, because when you're finding the domain, it's a lot easier to find the domain if you are working in this unsimplified form. So let's work on now finding the domain. So for this first one, the only thing that can go wrong is if 7x minus 4 plus 4 is equal to 0. So let's see what happens. So if we have 7x minus 4 plus 4 is equal to 0, we get that 7x is equal to 0. So x is equal to 0 is the only thing that can make this function not be good. So we don't want a 0 in the denominator. So what this means is that our domain for f of g of x is going to be negative infinity to 0, and then 0 to infinity. Okay, for the next function, g of f of x, we have 7 times x over x plus 4 minus 4. So the only problem we can have with this function is, again, if the denominator is 0. But our denominator in this case is x plus 4, so we want to find out where x plus 4 equals 0. If we subtract 4 to the right, we see that that's just at negative 4. So for our domain, the only point we want to skip over is negative 4. And so our domain would look like this. For f of x, we want to again consider the denominator here. Now this one's a little tricky because we have a fraction inside of a fraction. So we know that we already can't have the point negative 4 because of these little fractions here and here. But we also need to figure out, where does this entire denominator, let me change my color here. So this denominator here, we also need to figure out where it is equal to 0. So let's do that. That's going to take us a little bit of work. Okay, so we have x over x plus 4 equals 0. So we can subtract 4. So we have x over x plus 4 is equal to negative 4. And then we can cross multiply. So we'll have negative 4 times x plus 4 is equal to x. And if we distribute, we have minus 4x minus 16 is equal to x. We can add the 4x over, so we have minus 16 is equal to 5x. So x is equal to negative 16 over 5. Okay, so this is one other number besides negative 4 that we cannot have plugged into f of f. So let's write this as an interval. So we can go negative infinity up to negative 4. And then negative 16 over 5, just for reference, is, let's see, that's about 3.2, so negative 3.2. So we can go from negative 4 up to negative 16 over 5. And then we can just go from negative 16 over 5 up to infinity. So we just want to make sure we leave out those 2 points where the fractions denominators will be 0. Okay, and the final domain we need to find is g of x. Now compared to the other 3 we just found, this one shouldn't be too bad. So 7x minus 4, so if you look at this inside function, 7x minus 4 doesn't have any restrictions on the domain. So it's a line, so like y equals mx plus b. Those equations are always all real numbers. And since we're plugging that into itself, which is also all real numbers, the domain for this fourth one should just be all real numbers. Okay? We're going to do one more example with composite functions. So this time we're going to plug some numbers into our composite functions. So we want to find f of g of negative 2 and g of f of negative 2, and we're given that f is 3x minus 4 and g is 2 minus x squared. So to do this, we want to think about f of g of x as f with g plugged in. So we can think of it as f of g of negative 2. So unlike in the function question, so in the previous question we were worried about what do the functions look like. In this one, we're more worried about what is our numerical answer, so we don't have to actually get those complicated functions. We can sort of work them out step by step. So we want to work from the inside and go out. So the first thing we want to do is find g of negative 2. So to do this, we start with the function g, which is 2 minus x squared, and we plug in negative 2 in the place of x. So we get 2 minus negative 2 squared, which gives us 2 minus 4, which gives us negative 2. So now what we want to do is we want to take this answer that we got for g of negative 2 and we want to plug it in for f. So f of negative 2, again, we're not plugging in this negative 2 because it's here. We're plugging it in because it's the answer we got here. Okay? So f of negative 2 is going to be 3 times negative 2 minus 4, which is negative 6 minus 4, which is negative 10. So your final answer for f of g of negative 2 is negative 10. So the key with these, again, is don't go to the complicated formulas first. Make sure you work it step by step from the inside out. All right, we're going to do one more. So we're going to find g of f of negative 2. So this is the same idea, except now f is the thing we're going to find first. So f of negative 2 is what we want to find first, and we kind of just found that, but I'll do it again. So we have 3 times negative 2 minus 4 is equal to negative 6 minus 4, which is negative 10. So we're going to take this answer from f and plug it in for g. So we'll have g of negative 10, which is 2 minus negative 10 squared, which is 2 minus 100, which is negative 98. So negative 98 is your final answer.